Hello, my name is Yusuke Naito, working for Mitsubishi Electric Corporation Japan. So today I'm going to talk about the multi-user security or MAC's peer universal hashing in the ideal cipher model. Okay, so the message authentication code or MAC is the target algorithm of research. MAC is a secret key algorithm. And okay. So right figure shows the interface of the MAC algorithm. It takes arbitrary length message as well as the secret key. It returns the fixed length tag. MAC is used to authenticate data or generate a pseudorandom string. For example, the right bottom figure shows the authentication protocol with the MAC algorithm. So first, secret key is shared between the Alice and Bob. Alice is the sender and Bob is the receiver. And first, Alice derive a tag by using the MAC algorithm with the shared secret key and a message, and sends a pair of message and tag to Bob. After receiving the pair of message and tag, Bob derives the tag T prime by using the MAC algorithm with the shared key and the received message. So if the T equals T prime, then the message is authenticated. Otherwise, it is invalid. Okay, so regarding MAC design, the MAC has mainly designed by using block ciphers such as AES. And many block cipher-based MACs follow the HT type structure, as shown right figure. And for example, these CBC MAC, CMAC, and ZMAC uses HT structure. So in this HT structure, first, the keyed hash function capital H is performed that takes arbitrary length message, capital M. Capital L is a hash key. And then in the outer part, the block cipher capital EK is performed with the block cipher key capital K that produce the tag T. So HT structure ensures the design simplicity, efficiency, and simplicity of proof. For example, CBC type MACs have the HT structure. The right side part shows, for example, right side figure shows the EMAC structure. And this structure is quite simple because the hashing part is just iterating the block cipher. The construction is CBC hash function, and the construction is efficient. So for each message block, capital MI, a block cipher is called only once. And regarding the security proof, HT is a secure pseudorandom function if the underlying hash function is a universal hash function. This feature, the proof becomes quite simple. So regarding the security goals, the PR security of HT-based MACs have mainly been analyzed in the single setting. And in this talk, the key size is k-bit and the block size is n-bit. And the block cipher with a k-bit key and NP assumed to be a secure pseudorandom permutation. And in this assumption, the single PR-free security advantage is introduced, which means the k-bit offline security is assumed. And in the security game, the right figure shows the PR-free security game in the single user setting. In this game, adversary interact with the HT structure in the real world and random function in the ideal world. So, and by online queries. So adversary goal is to try to distinguish between the HT and the random function. And it was proved that this construction is a secure PRF up to this bound. So from this result, the security result, we can focus on designing the key hash function in HTE so that the probability epsilon is close to the another probability. Recently, multi-user security has gained attention in the research of symmetric key cryptography. Multi-user security captures the real-world attack scenarios where adversary targets a particular service rather than a particular user. So in the multi-user setting, adversary can access multiple users like this figure. So this figure shows the multi-user PRF security game. So in the real world, adversary interact with U instances of HT, and in the ideal world, adversary interact with U instance, U random functions. So U is the number of users. So compared with the single user adversary, multi-user adversary can obtain a lot of information for attacks. So indeed, the multi-user security of Cerebral Max degrades from the single user security. So designing a Mac without such security degradation is an important research topic for symmetric cryptography. So regarding the upper bound of the security level of Mac, there is a genetic attack that recovers one of the user's keys with 2 to S over U query complexity. S is the key size of the target Mac algorithm, U is the number of users. So in this attack, first the adversary makes online query to each user with zero string message. So in the online phase, the adversary can obtain UMAC tags from each user. And then the adversary guesses 2 to S over user keys, sorry, case mistake, 2 to S over user keys, and for each guess keys, the adversary calculates the tag of the zero message. So in the offline phase, 2 to S over U guessed tag is defined. So from these tags, we can obtain the 2 to S pairs of the online tag and offline tag. So since the key size of the Mac is S bits, so we can expect that at least one guess key is equal to the one of sum of user keys. So this equation can be confirmed by checking the tag collision T called T star. So regarding single key HT schemes, that is key size is equal to the block size of key size. The security level is at most 2 to S over U due to the genetic attack. So 2 to S K over U, the number of users. So the K-bit security cannot be a K-bit security which is ensured in the singular setting cannot be achieved in the multi-user setting. So to achieve the K-bit security, HT must have 2 or more keys for block cipher or other primitives. So we consider HT type marks such that the hash key capital N and block cipher key capital K are independent. So regarding the assumption for block cipher, the singular security of HT rely on the SPRP assumption. And however, in the single setting with U users, there are at most U block cipher keys. So with this assumption, the in the security proof, the U block ciphers are replaced with the U random permutation. So by this replacement, the U PRP advantage functions are introduced in the security bound. This means U security loss arises. So the offline security is reduced according to the number of users. So the existing work, in order to avoid this such degradation, the existing works evaluate the multi-user security in the ideal cipher model. So in this model, block cipher is assumed to be an ideal cipher, and in this model, adversary has access to ideal cipher by offline query, like this figure. And of course, in HTE construction, the block cipher values are evaluated by using the ideal cipher. So regarding existing work for multi-user security in the ideal cipher model, both et al. Prove that the multi-user security of HT does not degrade from single security. Their proof assumes that the underlying hash function is epsilon universal hash function. So this means that the collision probability is bounded by epsilon. And also they assumes that the underlying block cipher is ideal cipher. So with these assumptions, they prove that the offline security is 2 to half of n, and offline security is 2 to k. So there is no security degradation. However, their definition of the universal hash function does not cover the ideal cipher query. This means that their security band covers only the non-block cipher-based hash function, like polynomial hash function, and does not cover block cipher-based hash functions, such as the CBC hash function. So in order to cover the block cipher-based hash function, we define new security notions for block cipher-based hash functions that is alternative to universal hash functions. So, and cover offline queries. So in our new security notion, we introduce adversary that make an offline query to an ideal cipher, and adversary returns the message of hash function. So we define the two security notions, epsilon1 regular in the hashing in the ideal cipher model, where the adversary goal is to find a message and its output of the valid message and valid output of the hash function. And the next security notion is epsilon to almost x by universal hashing in the ideal cipher model. So the adversary goal is to find a message pair with this collision. So using this notion, we derive this security bound, and capital QU is the maximum number of online query to a single user, and Q is the number of online query, and P is the maximum number of offline query. So this term ensures that the bound ensures that offline security is to k bits. So the remaining goal is to find a hash function such that the epsilon1 and epsilon2 is almost optimal security, almost optimal probability. So we show that regarding the CBC hash function, we show this security bound, and by using this bound, we obtain this security bound. Bound of HCBC, that is EMAC. So this bound shows that offline security is k bits, and online security is half of n bits. So this bound shows that the multi-user security of EMAC does not degrade from the single security. So HT require two block cipher key capital A and capital K, which should be independent. So HT performs the key schedule twice and require memory key to keep two subkeys. So we consider a variant of HT, HTXE, which uses only a single block cipher key. So it improves the efficiency regarding the memory size and the speed compared with the HTE. And however, there is due to the generic attack, so we need another key capital L. So we use independent key capital L in the middle state of the HTXE. So that right figure shows HTXE structure, and the middle state is used. The independent key capital L is used in the middle state. This topic was initially studied for the CBC type marks, HCBC and TMAC. So evaluating the multi-user security of HTXE is a natural extension of these works. So for this construction, we derived this multi-user security bound, and this bound means that HTTP achieves the same level of security as HTE. And by combining with CBC bound, we obtain this bound, and HTE with CBC includes XCBC and TMAC. So this bound shows that the offline security is k-bit and online security is half of n-bit. So that is the multi-user security of XCBC and TMAC does not degrade from the single-user security. Okay, so this is conclusion of talk. We consider multi-user security of HT and HTXE, and we propose security notions for hash function epsilon1 regular hashing in the ideal cipher model and XU in the ideal cipher model. And we derive these security bounds for HT and HTXE. And we also derive the security bound for CBC, and by combining these bounds offer the security bound of EMAC, XCBC, and TMAC. So we can conclude that the multi-user security of EMAC, XCBC, and TMAC does not degrade from the single security. Okay, that's all. Thank you very much.
That was interesting, thank you. Just a general question is, where is this being proposed?
Sorry?
Where is this being proposed? Is it going to NIST or the notions that you're describing here?
So your question?
These have not been proposed yet, right? And are they, yeah.
NIST?
Are they published or proposed in NIST? NIST? I can't catch your question. So. Well, these are proposal, right?
Yes, well, I propose two security notions.
Yeah.
And it is new in
Right.
the ideal cipher model. So, and I apply the new notion to the existing scheme.
Okay.
So,
Perfect. Thank you.